Today we're going to be working with optimization, which will require us to translate some word problems, and then we're going to be looking for the mins or the maxes, and that's what optimization is all about. When you're working with an optimization problem, you're trying to find the maximum product or the minimum cost or maximum revenue, income coming in, things like that. So they're very obvious sort of application problems. And so I'm going to start real general. What if I'm just working with numbers in general? So one number is 10 more than twice another number. And so I have to consider what I'm thinking about here. One number, maybe I'll call X the one number. And then the other number will be 10 more than twice that one. Okay, so I have a number, and then 10 more than twice that number is my other number. So now I have my two values that I'm looking at, a number, and Y is the other number. Now, it really doesn't matter which one I call X and Y. I'm just putting in place values for these kinds of things. So now I need to figure out what my X and Y are. I have these two numbers. I need to figure out what my X and Y are so that they have a minimum product. Well, product means, and the function that I'm looking at, I'm going to call my function that I'm trying to minimize in this situation is going to be the product of X and Y, so X times Y. Now, when I'm talking about finding a minimum or a max, finding my relative extrema, I need to take a derivative, but we haven't yet learned how to take a derivative on two separate variables. And so that's where this thing comes into play. I have Y in terms of X, and so I can replace Y with that X expression. And now I have just a polynomial with one variable, and I can take my derivative. So f prime of X is 4x plus 10. Now, when we were doing our minimum and maximum, when we were finding our extrema, relative extrema, what we did is we set it equal to 0, because that was when the graph, remember, changes direction. F prime is the tangent line, and I want to find when that tangent line is 0, because that's when I have a low point or a high point. I want to figure out when the slope is 0. So I'm going to set this equal to 0 and then solve for it. And if I subtract 10 and divide by 4, I will get 5 halves for X, actually negative 5 halves. So subtract 10, divide by 4. So negative 5 halves is my X. What I like to do is to make sure that negative 5 halves is in fact the minimum that I want it to be, because if it's not, then I either am not able to solve this or my minimum comes at an end point. And that's actually more of a calc topic. So most of the problems that we're going to have, if we find a value, if we did it correct, it will come out to be the minimum or maximum that we want. There are going to be situations, however, where I get two answers and I'm going to have to decide which one is the min or the max, depending on the scenario. But anyways, I'm just going to check, just like we did before, my f prime here and see if this is in fact the minimum that I want it to be. And so I do my test points right in here. So let's say I put in something to the left of negative 5 halves. I'm going to just put in negative 10. And negative 10 is going to give me a negative result, because that would be negative 40 plus 10. And then I'll put in something to the right, like 0. And that would be 0 plus 10, so that's positive. That means that up to negative 5 halves, it's decreasing, and then after negative 5 halves, it's increasing, and that should be a very apparent min at that value. Okay, so I found my minimum. My minimum happens when X equals negative 5 halves, but I do need to find the two numbers, so find the numbers such that, so now I need to find Y, and Y is 2 times whatever X is, plus 10, and so that would be 5 when I do the math on that. So my numbers are negative 5 halves and 5. And that would be my final answer for that problem. So now this one was a real general one. Like I said, we do a lot of application problems with these, where it's an obvious application to a scenario. This is not an obvious application to any scenario. It's just sort of playing around with numbers. But if I can put it to a story, it becomes a little more obvious. And so here we have a cryptography expert who's deciphering a computer code. And in order to do this, he needs to minimize the product of a positive rational number and a negative rational number. So I have two numbers being multiplied. We do know that the positive number is exactly 7 more than the negative number. So if I call x the negative number, negative, can I spell that right, number? Then y would be the negative number plus 7, because it says that the positive number is exactly 7 more than the negative number. So I have my negative number, and then 7 more than that is my positive number. And so again, what I'm doing is I want to minimize the product, so I need to do the product again. My function is going to deal with the product of x and y. But again, I do not want to have the two variables in it, so thankfully I have y in terms of x, and so I can replace my y with that x, and I'll multiply that through, so I have a nice polynomial function that I can take a derivative on. Once I'm there, it's my derivative, f prime of x equals 2x plus 7, and I set it equal to 0. And solve. So I'll get negative 7 halves for x, minus 7 divided by 2. And again, I like to just make sure that that is truly the min that I want it to be. So I'll do my test points just like we've done in the past. I'll plug it into that derivative here. And I'll use something like, again, I'm going to go obvious to the left, negative 10. So that would be a negative value. And then obvious to the right, that would be maybe like 0, so that would be a positive value. So again, decreasing and increasing definitely makes that the min that I want it to be. So my last move is x is negative 7 halves, and y is negative 7 halves plus 7, because it's x plus 7. So my value for that is, I believe, 7 halves, I'm pretty sure, because that would be 14, yes, so 7 halves for sure. And so my numbers are negative 7 halves and positive 7 halves. Now, I do have to be careful when I'm answering the question, because in the last one, in the previous problem, the first problem we did, it said find the numbers. And so that's what I did, I found the numbers. But in problem number 2, it says, what is the final product that the expert is looking for? That means that I have to take those numbers and multiply them together. And so my final product is negative 49/4. Final product is what he's looking for. All right, so I'm going to pause the video, and what I want you to do is try number 3. It's the same problem, and then when you're done with that, you'll pause as well. When you're done with that, turn it back on and check and see how you did. All right, so welcome back. I hope that went all right with you. So it was really pretty much the exact same problem. We just changed the number to 5 instead. So I defined my variables, set up my function, went ahead and multiplied that through. Then I did my derivative, made sure that set it equal to 0 and solved, made sure that it was in fact a minimum, and it did come out to be a minimum. And then I actually went through and answered the question. And so again, it needed the final product, and the final product was negative 25/4. So the first 3 problems were very similar, 2 specific to a cryptography expert. The first one was just kind of a general problem, but they're not all going to be exactly like that. We're going to see some application problems that that vary, obviously, depending on the scenario that we're looking at. So let's kind of continue on. Up next, we've got a farmer. The farmer wants to construct a rectangular pig pen using 500 feet of fencing. The pen will be built next to an existing stone wall so that only 3 sides of fencing are going to be needed to enclose the pen. And so what dimensions should the farmer use to construct the pen with the largest possible area? So this time I'm doing a max, whereas in the previous problems I was trying to minimize a product. So this is a max going on here. And so I'm going to set it up. I've got the wall that I'm building right here, my pen next to. So I'm going to put some fencing around here. And they said I only need to put fencing around the sides, the 3 sides. And so I have 500 feet of fencing total. So x plus y plus x is going to be the fenced in area. X plus y plus x. I want to use all 500 feet. Of course, I want to use as much as possible in order to get the largest possible area. It doesn't make sense for me to only use 400 feet when I have 500 feet to use. So I'm going to maximize the area. I want to use all 500 feet of fencing. So what I have here is an expression in terms of x and y, actually an equation in terms of x and y. But that's not what I'm trying to maximize. I'm trying to find the largest possible area. And so my function that I'm going to be working with actually has to do with area. And how do you find the area of a rectangular space? I'm trying to figure out how much space I have in here for whatever it is. What is he doing? A pig pen, okay? And so the area is the length times the width. And it doesn't even matter that there's a wall here. It still is a length times the width for the area in there. So xy is going to be my area. This is where I run into that same problem that I ran into before, and that is I have 2 variables, and I have not learned how to take a derivative on 2 separate variables. You'll learn that in calculus. But right now we haven't done that, so I need to use this guy here to help me out. I want to get y in terms of x or x in terms of y, and so I'm going to solve this. Y equals 500 minus 2x. And I'm going to use that to plug into my formula. So when I put that into here, then I'm down to the one variable that I want. And again, this should look really familiar to the last one. I can just distribute that through and then take my derivative. So a prime of x, I just chose a instead of f because I'm not using an in general function, I'm doing the area function. So area, you can do whatever you want, obviously there. And so minus 4x, again, I set it equal to 0 and solve. And so it looks like x is going to be 125. However you need to do that algebra, that's not what I'm teaching you here, but subtract the 500 and divide by 4. So 125 is my x. Again, I am going to make sure that that is in fact, 125, watch what I'm writing. That is in fact a max because that's what I want it to be. So if I plug in something like 0, I'll get a positive value. If I plug in something like 200, I'll get a negative value. So that's increasing to decreasing. It is indeed the max that I want it to be. So my directions say what, or my question that I'm answering here is what dimensions should I use? And so what dimensions should the farmer use? Well, x is 125, in this case, feet. And y is 2 times 125, nope, sorry, 500, my goodness, get this straight here. I'm using this. It is 500 minus 2 times 125, and so that ends up being 250. Oops, and you can't see that. Boy, oh boy, get with it, lady, hey? Okay. Get on it. All right, so my dimensions, I would write this as 125 feet by 250 feet for my final answer on that one. So those are the dimensions that I want to make that pen. Again, that all the problems aren't going to be exactly the same, and so, but they're going to work with maybe some similar things. We'll see a lot of area and perimeter connections. In the future, we'll see some area and volume connections. But here's another area and perimeter. But in this case, we have a rancher, and the rancher wants to construct two identical rectangular corrals. And so they are going to be adjacent to each other. And so that means they're going to share one side of fencing down the center. What dimensions should the rancher use to construct a corral? Again, we want that will enclose the largest possible area. So again, I want a max. But I don't have a wall that I'm building it against. I just have these rectangular corrals, and the rectangular corrals share a fence. So they're adjacent right next to each other. And the question is, what dimensions should the rancher use to construct each corral? So I want each individual corral labeled. So this is X. This length would also be X, and the far length would be X. And let's call these little pieces Y. All right? So when it comes to the amount of fencing that I'm using, 300 feet of fencing, I am going to be doing X plus X plus X, so 3X, Y plus Y plus Y plus Y, so plus 4Y, and I want to use the total 300 feet of fencing. Because I want to maximize the area function is the one that I'm going to be working with. Now I have to be a little bit careful because area, remember, is length times width. And so my length is this X, but my width is actually 2 Y's, that total width. So my length is X by 2Y. That's going to be my total width on this. All right, again, two variables. I only want one, so I'm going to solve this one in terms of Y, so I can replace Y. So I would subtract the 3X and then divide everything by 4. So Y is 300 fourths minus 3/4 X. Or better than that, I'm going to simplify this down. 300 divided by 4, that would give me 150 halves, so 75 minus 3/4 X. So when I rewrite this, I'll have 2 times 75 minus 3/4 X. And so my area is X, that would be 150 minus 3/2 X. And I will distribute that X through, so 150X minus 3/2 X squared. Now I will go ahead, I kind of ran into some ran here, but so I'll just kind of curve this down over. My derivative will be 150 minus 3X. And so when I set that equal to 0, 150 minus 3X, I end up with X equals 50. So again, my X is 50 feet, but I want to make sure that that is in fact the max that I want it to be. So I'll check it in, let's see, my A prime is right here, so I'll check it in this one. And I'll put in something like 0, so 150 minus 0 is positive. And I'll put in something like 100, and that does come out to be negative, so that is a max that I want it to be. So I check to make sure that that did come out to be a max, and then I'm going to answer the question, what dimensions should the rancher use to construct each corral? So I want the each corral dimensions. I have the X. X is 50 feet. And then Y, my connector right here, Y is 75 minus 3/4 times 50. And so when I do that math, let's see, I'm going to get, I'm just going to cheat and use a calculator because my brain doesn't feel like thinking right now. So I do 75 minus 3 fraction 4 times 50, and I get 37.5 feet, it looks like. So my y is 37.5 feet. So my dimensions are 50 feet by 37.5 feet. And that should be my final dimensions for that problem, 50 feet by 37.5 feet. Okay, so again, it's not restricted to just those types of problems, and we're going to get into one last problem that deals with a cell phone company selling a new type of smartphone. So in this smartphone problem that we have here, we have a company that's selling a new type of smartphone at the price of $160 minus 5 cents for every phone made, where X is the number of smartphones manufactured in a day. The parts for each smartphone cost $60. That's each. That means the company's going to pay $60 just to produce this, and then they're going to sell it for this cost to you. And then the labor and overhead for running the plant costs $7,000 per day, and we need to figure out how many smartphones we need to use so that the company manufacture and sell per day, so that we can get a maximum profit. Again, so we're trying to maximize the situation. Now, in this scenario, I don't have a picture that I can draw like I had in the previous two problems. And I don't even have a second variable involved like I did in all of the previous problems. In this problem, all I have is one variable defined. That is, X is the number of smartphones manufactured. And so we need to figure out how many are going to make them or give them the highest profit. Obviously, it doesn't make sense to only make one. You're not going to make a lot of money off of them, but there is a point where you make too many, and as a result of making too many, you take too much off of the price, and that leaves you with not making enough off of each smartphone, and you end up losing profits in the end. So we want to find that perfect place where this function, when graphed, comes to the high point of profit before it starts dropping down. This is where we want to be as a business owner. We want to maximize the profit. So I've got to set up my profit function. Again, I only have one variable here. So I'm going to start with, what am I going to make per phone? So they said that they're going to charge $160 minus 0.05x per phone. So yes, I know there's an X here because they're able to take a certain amount off for each phone sold. If they only sold one phone, they can cut the price by a nickel. If they sell 10 phones, they can cut the price by 50 cents. And so this is going to be the price per phone times the number of phones sold. But they do have to consider the fact that they're going to pay $60 just to make the phone, to buy the parts. So $60 each phone. And then they're also going to have to remove the fact that it costs them $7,000 a day just to run their plant, to pay for labor, buy the product, all of those kinds of things. Heat the building, everything that comes involved in running a company. And so this is my new profit formula. So the profit is, I'm going to clean this up a little bit, 160x minus 0.05x squared minus 60x minus 7,000. And then again, I'm going to clean this up a little bit more because I've got some terms that can be multiplied. And I'm also going to move it around so that I have the highest power first. So I have negative 0.05x squared plus 100x, that was 160 minus 60, minus 7,000. Now I have a nice, again, polynomial function with one variable that I can take my derivative on. So P prime is negative 0.1x plus 100. And that looks like that's it for that. So I'm going to bring this over here, set that equal to 0, and solve. It looks like when I solve, I would get x equal to 1,000. Again, subtract 100, divide by negative 0.1, it looks like 1,000. So at this point, it looks like they should be making 1,000 phones to get the best profit margin here. I do want to make sure that this is in fact a max. And that's just my safety check for me. It kind of helps me realize if I made a mistake. If it doesn't come out to be a max, maybe I had an error in this problem somewhere, or maybe this function is just not even a reasonable function and not solvable. So I'll plug in 0, and that gives me a positive value. And then I'll plug in something to the right of 1,000, like 2,000. So that would be negative 200 plus 100, that's a negative value. So increasing, decreasing, that is a max. And so now I want to make sure that I actually answer the question that they are asking, and they say, how many smartphones should the company manufacture? And I'm going to say 1,000 smartphones. All right. So that is it for these word problems, and then we're going to figure out what homework that you need to do. So get out your homework packet and I will ramble off the problems. So on your homework packet, I'm going to have you do problems 1, 2, 3, 7, 9, 10, 15, and 23. Now look closely. All of them are going to be very similar to problems that we did in our examples. So when you start to read the problem, if you look at problem number 1, that's like examples 2 and 3. Problem number 2 is like example 4. Number 3 is like example 5. You get what I'm saying here. So just kind of follow along and double check, and then it'll repeat over. You'll have some other you'll do a couple where you have the rancher, and a couple where you have the cryptographer, and a couple smartphones. So give it a try, take your time, use the notes as guidance, and I will talk to you all tomorrow.